Alright, chemistry. We're back at it. Second semester. Midterm totally happened, kind of. Obviously there were some snafus with my CPA. Actually, apparently it was like issues with the internet in general. The internet is just like this weird thing. If you cut a cable, it just stops. So there's very little that we could do about that. For those of you who didn't finish, it doesn't affect your semester average. For those of you who did finish, it only affects your semester average if you did well on it. So like it's kind of functionally extra credit. I have no control over that. That was um, like the my CBA situation was totally out of our hands. So there's basically nothing we could have done about that. There's going to be a separate video talking about the all the questions, right? So I'll still go through the whole test. I'll go through all the questions. Overall, for the people who were able to finish it, and like the people, and I looked even at the people who didn't finish it. I looked at the answers that y'all had. For the most part, it went reasonably. There are a few things that obviously I'll go over, but that's in a separate video. Just as a reminder, like check the announcements, right? Check these. Something will go up here for this week. I'm making this video a little early, which is why there's no, if we look, I'm making this on the 31st. There's something scheduled here, so that's why nothing is up for this week, first week of February. Now, even though I haven't done this in class yet, I'm trying to be a little proactive. So, let's check this out. New semester. I'm gonna fly through a little bit of this. This gases section is not super terrible, so I want to get through this, and I want to get through thermochemistry in the next week or so. I'm being a little ambitious, but I think you guys can handle it. Let's just get to it. Let's do this thing. So gases are special, right? And there's a reason that they're kind of their own little section here. Solids and liquids don't get their own sections, only gases. So there's something very specific to know about gases. This first line and the second line are important. They tie back to moles. Sorry, moles are not going anywhere. They're not going away. Something to remember stuff about them. But at the same... Oh, hello. New semester, same old pen. At the same temperature and pressure, then equal volumes of any two gases will contain the same number of particles. This is known as Avogadro's law. Avogadro, just another scientist guy. Actually, the number for the mole, 6.02 times 10 to the 23rd. We occasionally refer to that as Avogadro's number. He did a lot of work with moles, but for any two gases at the same temperature and the same pressure and the same volume, right? So we're saying that they're the same temperature, same pressure, same volume. Two gases with those things being the same will also have the same number of particles. It's the same amount of stuff, basically. And the big deal, another mole relationship, right here. 1 mole of gas, of any gas at STP will occupy 22.4 liters. Now, STP is a term that has come up a couple of times. I said it's standard temperature and pressure. So I'm going to immediately kind of jump down to this last bullet point. STP is standard temperature and pressure. That temperature, standard temperature, is 273 Kelvin, 0 Celsius, 32 Fahrenheit. So it's actually the freezing point of water. And standard pressure is 1 atmosphere, which is what you feel right now. You don't perceive it, right? But the pressure that you're under at all times is just 1 atmosphere of pressure. It's on table A of the reference table. It has it in the temperature in both Kelvin and Celsius. It has the pressure in atmospheres and something called kilopascals. We'll kind of get into that. Now, our rules for gases, right, only depend on the fact that they are at the specific temperature, specific pressure will tell you these conditions. Usually it'll be STP, right? The rules for gases, the laws for gases do not depend... Oh my goodness. Is this calibrated wrong? What's happening here? There we go. Alright, we're on the line now. They do not depend on the identity of the gas. It doesn't matter what kind of gas you have. It just requires that the gas behaves ideally, which is why we use standard temperature and pressure. STP is, they're not super ideal conditions, but at STP we at least know that they're going to act a certain way. When we look at gases, we usually describe them in terms of pressure. So if I'm talking about a sample of gas, I'll probably describe it as having like an atmosphere of pressure, or 3 atmospheres of pressure. There are a lot of different units for pressure. Millimeters of mercury, pascals, kilopascals, and atmospheres. I'll tell you that atmospheres and kilopascals, those are the 2 most common. Atmospheres, I think, are the most common overall. 1 atmosphere is 101.3 kilopascals, is 760 millimeters of mercury. The mercury one has fallen out of favor just because it's an awkward unit, and it's an awkward number to remember, 760. 101.3 kilopascals is on your reference table, but again, more commonly you'll just be using atmospheres. Now, because STP has numbers, right, 273 Kelvin, 1 atmosphere, in the same line as, like, if you see atom, that's like protons equals electrons, this bit here, if you see STP, you should probably do yourself a favor and give yourself 273 Kelvin, 1 atmosphere, in case you need them. You might not need them for the question, but if you do, you have them, alright? Now, there is a little bit of stoichiometry, there is a little bit of mole work here at the bottom of 47. I am temporarily going to skip over it because it has been a very long time, I mean a very long time, close to 10, 11, maybe 12 years since a gas stoichiometry question has popped up on the Regents. I don't want to like clutter you. I don't want to overload you here with stuff, more stuff on moles. You know, the mole stuff that you have, the stoichiometry, like the ratio of the coefficients in the equation, and the conversion of moles to mass using the GFM formula on the back page of the reference table. That should be enough moles work. I'm going to try not to clutter you with that. So I'm actually going to move straight on from page 47. We're going to head over to page 48. We're going to continue talking about properties of gases. Specifically, properties of ideal gases, even though not every gas is ideal. We like to study them as though they are, mostly because it simplifies things, right? So ideal gases are theoretical. No gas actually no gas actually acts like an ideal gas. However, if they were to act like an ideal gas, we know certain things will be true. And we can even use this to study real gases as long as we understand, like, this is what should happen, and we observe this, which is not exactly the same, but the reason it's not exactly the same is because we've changed this condition from the ideal gas situation. So an ideal gas is a theoretical gas under conditions of high pressure. Nope, that's wrong. High temperature, my apologies. You want a high temperature and you want a low pressure. Right? The biggest reason for that, gases are able to move freely. They have no definite shape, no definite volume. Their particles are just here, there, and everywhere, right? We want those particles to be able to move as fast as possible, and we want them to be able to move in as much space as possible, which is why we want them to be under high temperature. High temperature means they're moving very fast. We're giving the particles a lot of energy. Again, temperature is average kinetic energy. So if they have a lot of average kinetic energy, they're moving very fast. That's one of the things that we want. Low pressure means that we're not cramming them into this small space. Low pressure implies that we have this large space for the gas molecules to roam around in. It's also very good. Right? There are 2 gases that kind of act like ideal gases. They are hydrogen and helium. So they're 2 very light gases. They're GFM, right? Hydrogen has a GFM of 1. Helium has a GFM of 4. So they're very light. They behave like ideal gases because they're as close to a very small particle that moves very, very fast as we can get. Now, the kinetic molecular theory. This is our understanding of how gases work, right? So this is, what do we understand about gases? Well, we understand them with respect to the kinetic molecular theory. This is what we're pretty sure an ideal gas would do, and it's what most normal gases do. There are slight discrepancies, but for the most part, gases will do all of these 6 things. Gas particles have mass, but they have negligible volume, which means the volume occupied by a gas is essentially the volume of the container. And this is something that you already know. Right? Gases occupy the volume of the container that they're trapped within. Right? The particles don't actually have a reasonable, meaningful volume of their own. They just, whatever volume they're in, that's their volume. Right? Gas particles move randomly in straight line paths. Right? They don't orbit things. Right? They don't travel in orbits. They don't travel in circles. They don't like wibble wobble back and forth. They pick a straight line and they do that, and then they hit a boundary, and then they bounce, and they go in a new straight line. They hit a boundary. They bounce. It's like that screensaver thing, right? But they'll go in a straight line until they can't anymore, and then they'll bounce and they'll hit something else. They'll bounce and they'll hit something else, and they'll bounce and hit. It's like that, right? So that's what we mean random straight line paths. They pick a straight line. It's not dependent on anything else. They're not subject to any attractive or repulsive forces, which is to say they don't naturally go towards each other, and they don't naturally repel each other away. All collisions are elastic, which means that kinetic energy is conserved. Elastic collisions, these are like perfectly elastic collisions, technically, if you get to next year. If you take physics next year, it's another thing. But elastic collision implies that all the kinetic energy is conserved, so they don't lose energy when they bounce off each other, which is something, again, that you should be familiar with, right? Conservation of energy. However much energy there was before the collision is all there after the collision. They might, like, flip-flop. If this one's going really fast, this one's only going slow, then they'll probably flip-flop. This one will start going slow, this one will start going really fast. The pressure exerted by an ideal gas is related to the number of collisions the particles make with the walls, which basically just says the pressure that you feel from a gas is just based on how many collisions do gas particles make with you, right? The reason you feel 1 atmosphere of pressure is because the air molecules that are contacting you hit you with 1 atmosphere's worth of pressure. If you were to feel more pressure, it's because more air is hitting you. And then finally, the absolute temperature of an ideal gas is directly proportional to the, you know this definition, average, I'm going to abbreviate average kinetic energy, but that's here. Temperature is still proportional to average kinetic energy, which is the graph way down at the bottom here of 48. Hello? There we go. We'll use this theory to kind of look at questions and understand how they work. But if you think about it, reducing the volume of a gas at constant temperature increases the pressure. Okay, reducing the volume means I'm squeezing it into a smaller space. If they're moving the same speed, if we keep the temperature the same, right, so we'll squeeze them into a smaller space, and they're still moving just as fast, they're going to hit stuff more often. They're going to hit the walls more often, which means the pressure will go up, right? So squeezing it into a smaller space increases pressure. This is like if you take a balloon that won't pop, right? If you squish a balloon, it will get closer and closer to popping because you're trying to squeeze them into a smaller space. So that's the second bullet point, is just explaining that, right? The last thing that hello, don't do that. There we go. Last thing I'll talk about today is some equation work, right? We're going to use the stuff from kinetic molecular theory to talk about how real stuff actually acts. And like I said, we use the ideal situation to kind of view real life situations, right? So real gases might be ideal, might not be ideal. It depends on the environment. If you want something to behave ideal, you want high temperature, you want low pressure, right? So we are again going to repeat that. High temperature and low pressure will enable a real gas to exhibit almost ideal behavior. When we are working with these gas laws, which we're going to do, it's a little bit of equation work, you have to use the Kelvin scale. If you're using temperature, you have to use the Kelvin scale, right? Now, the first of these laws, oh goodness, We're not, there we go, now we're moving. The first of these laws is called Boyle's law. You don't need to remember the individual laws. You will want to remember these, like, relationships, right? What happens between pressure and volume? What kind of relationship is there between pressure and volume? So we talked about before. If I decrease the volume, squish it into a smaller space, I increase the pressure, right? So decrease in volume, increase in pressure. That is an inverse relationship. So P and V have an inverse relationship. That's this graph, right? It's the curve. It's not a straight line, it's a curve, right? Charles' law is a different set of relationships. It shows a relationship between, oh goodness, what's happening? Volume and temperature, assuming that pressure is constant, right? And this is a direct relationship because if you increase the volume, the temperature has to increase because they're able to move in more space. Short version, volume and temperature have a direct relationship. This is more or less how hot air balloons work. It's kind of the opposite. It's typically, as you change temperature, what will happen to volume. So if you increase the temperature, the molecules will be moving faster, and if the pressure stays the same, if you increase the temperature, you make them move faster, they're going to need more space to travel in to keep the same amount of pressure. This is the relationship that makes hot air balloons work, right? Hot air balloons rise because as they move faster, they expand. Because the balloon expands, the density is lower because it's the same amount of stuff in more space. Because the density is lower, it rises, is why hot air rises. But volume and temperature is a direct relationship, and that's this graph. It's just straight line, right? Now, the two of these two laws actually combine into something that we call, shocker, the combined gas law, right? This equation is on your reference table. It's on the back page, all right? Back page of the reference table has this equation. You do not need to memorize it. However, you do need to remember, and I want you to write this. Kelviv? That's not how you spell Kelvin. Use Kelvin for temperature. You have to use Kelvin for temperature. You just have to, all right? Now, there are practice questions here. What I'm going to do, I'm going to set the first one up, and then I want you to solve it, and then I'd like you to, hello? One day, the screen, there we go. Finish out the rest of these. That's kind of, that's your homework, right? So we'll go over this first thing tomorrow. First thing next class. So the gas left in a used aerosol can is at a pressure of 1 atmosphere at 27 degrees Celsius. If the can is thrown into a fire, what's the pressure of the gas? Wouldn't recommend doing this, by the way. All right, so let's set this up. So the first pressure that I read is 1 atmosphere. And then 27 degrees is a temperature. That's the first temperature that I read. That's 27 degrees Celsius. I need to convert that to Kelvin. I just happen to know that that's 300 Kelvin. The second pressure, what is the internal pressure? I don't know the second pressure, but the new temperature is 927 degrees Celsius. So 927 Celsius, well, that is 1200 Kelvin, right? So now I need to use the equation. The equation says P1 V1 over T1 equals P2 V2 over T2. Now you might be like, Kalimlan, hold up. You told me the equation has 3 things. We only have 2. Well, that's okay. And it's okay because what's going to happen here, I'm going to plug in the numbers that I have. So I'll plug in P1, T1, and T2. Because there was no mention of volume here, they never said anything about volume. What that means is that for this question, we don't need to worry about volume. I'm actually going to move this over just so I have a little more room. P1 V1 over T1 equals P2 V2 over T2, right? So the math that I'm doing here is 1 atmosphere over 300 Kelvin equals x over 1200 Kelvin. Now let's just solve for x. 1200 over 300. X equals 4. It's pressure, atmospheres. I know I said I was going to ask you to solve for it, but I figured I'd do the math with you. The trick with these questions is 1. Use the equation. 2. Convert to Kelvin. 3. Only use the information they give you. If they ignore a piece of information, then you don't need to worry about it. Right? Do your best to work on these questions. Remember that if you see a unit that you don't quite recognize, first thing that I would suggest to do is one day there we go. We're moving again. Check back, right? These are all the possible units for pressure. Temperature is going to be in Celsius or Kelvin. Volume will very likely be, in volume will probably be in liters. All right. So finish this out. 2, 3, 4, 5 here on page 50. We'll check it next class. This video has gone on for far too long, but new semester. Here we go. I told you I was going to start flying through stuff. We're going to start flying through stuff. I'll see you next class. Take care, kids.